Okay, one more example here in our applications of logs, and this one has to do with the half-life of a radioactive substance. So in this question here, we have this radioactive substance which has a half-life of 23 days, which is basically saying that if you take some amount of this material, 23 days later, exactly half of it will remain. And then after another 23 days, a half again will remain. So you're down to a quarter of the original substance, and so on. So what we're going to try to find here is how long it will take to go from 100 grams of this substance, which will be our starting value, down to 10 grams, our final value. And again, the key is the half-life over 23 days. Now the nice thing about a half-life is that kind of tells you what number to use as the base in your power. When you build your equation, you're going to use a base of 1/2 or 0.5. So here we'll let T represent the time in days for the 100 grams to decay down to 10 grams. And from that we will write our equation. So the equation, just as it was in example 1 and 2, will be the final amount, which is the 10 grams we want left, equaling some start value, which is 100 in this case, multiplied by the power. So the power has a base of 1/2 to represent half-life, and we know that half-life takes 23 days. So every 23 days is another half of the substance decays. So we have to divide the time by 23. And if you think about this, at 23 days, if T is 23, you have half left, because 23 over 23 would be 1. So 1/2 to the exponent 1 would be 1/2, and 1/2 of 100 is 50. So you go from 100 to 50 grams in 23 days. So now this problem becomes just like the last two. We have to obviously solve for T. So as we did in the last couple of examples, we'll divide both sides of this equation initially to get rid of the factor in front of the power. So divide both sides by 100. And that leaves us with 0.1 on the left equals to, well, we'll rewrite the base 1/2 as 0.5. And that is raised to the exponent T divided by 23. So again, the power of logs is that we can take the log of both sides here to bring down that variable that's in the exponent, so we can deal with it. So taking the log of both sides of this equation allows the exponent to be written down in front now. So T over 23 times log of 0.5 on the right side. And now we have to apply some algebraic skills here to isolate T. So the first thing I would do is divide both sides of this equation by log of 0.5. That'll get rid of the log of 0.5 on the right hand side. So you can cancel those out or cross those out. And then to get rid of the 23 in the denominator there with the T, multiply in the numerator by 23. But you must do that obviously to both sides. So the 23 will now cancel out. And you are left, if you think about it, with just the letter T, which is what you were trying to do, isolate T. So that's just some algebraic manipulation. Nothing too fancy there. So taking a calculator and multiplying 23 by log of 0.1 and dividing it all by the log of 0.5, you get approximately 76.4043. So that's telling us that it's going to take about 76.4 days for this to decay to the required amount of 10 grams. Now this did say they wanted the answer rounded to the nearest hour. So if we know there's 76 days, after the 76 we have 0.4043, and you can multiply that fraction of a day by the number of hours in a day, which is 24, to get approximately 10 hours. So the answer to this question is about 76 days, 10 hours for this radioactive substance to decay from the initial 100 grams down to 10 grams.